to go over the characteristics and graphs of polynomial functions and eventually use that understanding to sketch our own. And we're going to utilize Desmos to help with the technology when we need it. And then we're going to finish the lesson by using our understanding of all of the stuff we're talking about in this lesson and in a few previous lessons to write polynomial functions given a graph. Okay, so the first thing that I want you to see is that polynomial functions have no breaks, all right, and they must be continuous. So the things you're looking for when you're determining if this is a polynomial or not is you're looking for no sharp points, so no sharp points, and you're looking for no breaks. All right, so like the first one is very much a polynomial. This has like a jump, right, like a piecewise function going on here. So that's not going to be a polynomial. This one is not, if you remember from the previous unit, we talked about absolute value functions in this class. So this is absolute value function with that g. This one is a polynomial, and like the one above it, this last one is not because of that discontinuity there. The domain of polynomial functions is all real numbers. So you never have to worry about that if you know it's a polynomial. And we can use that understanding to help us find some zeros here and some intercepts. So this is kind of a continuation of the last lesson. So I'm going to show you again how to find those polynomials. Sometimes they'll already, or those zeros, sometimes the polynomial will be already factored, like in this first example. And then in the second example, you might have to do some of your own factoring. So let's find the y-intercept first. I always think that's the easiest. All right, so I'm going to plug in 0. So g of 0. So 0 minus 2 squared times 2 times 0 plus 3. All right, so that's going to give me a negative 2 squared, which is 4. And then this is times 3. So my y-intercept is 0, 12. Let's find the x-intercepts. Now, again, as I mentioned last lesson, you're going to set the entire function equal to 0. And this is really nice because it's already been factored for us. So we know we're going to have whatever makes these two factors 0 are the intercepts. So we have 2 and we have negative 3/2. Now, you're not going to need to know it just yet. We'll get to it later on in the lesson. But that x minus 2 raised to the second power is going to be something that is important. All right, that's called what we call a double root, or it has a multiplicity of 2. And that's going to mean something when we actually go to like sketch this graph. So, but for now, we just need to put that the x-intercepts are 2, 0, and negative 3/2, comma 0. Okay, let's try another one. This one will require a little bit more work because we're dealing with something we need to factor. So let's find the y-intercept first by plugging in 0. So f of 0, which is going to be 0 to the 6th power minus 3 times 0 to the 4th power plus 2 times 0 squared. When you have 0 to the 6th power minus 3 times 0 to the 4th power plus 2 times 0 squared, you know that this is going to be 0. So our y-intercept is 0, 0. As I mentioned in the last lesson, that means you know one of your x-intercepts will also be 0, 0. So let's set the entire function equal to 0 so we can do some factoring. All right, so I'm going to factor out, looks like I factor out x squared, which needs to be x to the 4th power minus 3x squared plus 2. We've factored a couple like these now, where if you think of it as x squared and x squared in your binomials, factors of 2 that add to negative 3 is minus 2 and minus 1. I'm going to keep factoring because I have the difference of 2 squares with x minus 1 and x plus 1. And now I'm ready to write down my x-intercepts here. So x equals 0. This one might be a little tricky. If you need to show the work, take your time to do it. I move it over in my head and make it x squared equals positive 2. Then take the square root of both sides to get plus or minus the square root of 2. Then x equals 1 and x equals negative 1. All right, so if I write down these as ordered pairs, I have 0, 0, square root of 2, 0, negative square root of 2, 0, 1, 0, and finally negative 1, 0. And that should make sense to you, right? If you count all those up, you have 1, 2, 3, 4, 5. You look at this, it doesn't match. That's because if you remember what I just mentioned, this root here, x equals 0, comes from this x squared term. So because this is what we call a double root, so a double root, when you add them up, you get 1, 2, 3, 4, and then the double root makes 5, 6. All right? So that matches our degree of 6. All right, that's some something good to know, especially as we move forward in this lesson. All right, so let's get into that now, since I've already mentioned it, talking about the multiplicity of these different zeros. All right, so it's going to come down to when you look at if it's already factored, it should be easy to tell, or when you're looking at the graph, you'll find out ways to do that as well. So the multiplicity is what I want to make sure I focus on. So let's make sure you know what happens when it's a single zero. This is completely cross the x-axis. A 0 with a multiplicity of 2, as I mentioned before, is a double root. We call this the touch and turn. And then when it has a multiplicity of 3, right, you'll notice this looks like a cubic function or a cubic 0 or root as you see it. So it does completely cross, but it has that kind of like inflection as it goes that makes that kind of S shape. Now, there is something that can be a little tricky when you're talking about, like, you notice that we have this touch and turn for a multiplicity of 2. How do you know if it's a multiplicity of 4 or 6? So it will just appear flatter when it touches and turns. And same thing with the cubic. How do I know when it's x to the 5th power, x to the 7th power? It will be more elongated, more flat. It's just really tough to tell. So when I do one of the examples that has that, I'll mention, like, you might have a different opinion on what's happening there. Okay, so I'm just going to use kind of this whole understanding and my understanding of other characteristics of polynomials to get into looking at these graphs and then eventually trying to graph them myself. So if I look at this first example, let's focus on this one, right? You'll notice I have a 0 right here at negative 3, and it's touching and turning. So I call this a double root. And then I have another root right here, which is completely crossing. And I don't see any, like the shape of the letter S. So I'm going to say that's a single root at x equals negative 1. And finally, my last root at positive 4, it does completely cross, but it has that kind of cubic or S shape. So I'm going to say this is a triple root. All right, and that makes sense when I look at this degree. So if I add 2, I'll do here 2 plus 1 plus 3 gives me 6. Now this degree is incorrect. I'm going to change it to what it should be. So if it's a degree of 9, right, this one right here, you can see it crosses and it has that kind of letter shaped like a letter S. So this is a triple root. Then we have this as a touch and turn. So it's a double root. And then our last root, what I notice here is that it does touch and turn, but it looks more flat. So I'm going to say this is a quartic root. All right, so that'd be 3 plus 2 plus 4. So 3 plus 2 is 5. 5 plus 4 gives me that degree of 9. Okay, so that's what I mean when it's kind of tough to tell, but this, see how it's more elongated or flatter compared to this double root. So that's why I made it the next set of even roots, so 4. Okay, now let's use all of that to help us sketch one of these graphs. And something that you would have done before, obviously we'll be using technology here in a moment, but we can do a lot of this without actually needing technology. So let's first find the y-intercept. So I'm going to plug in 0 and get 0 plus 3 squared times 0 minus 5. So that's going to give me negative 2 times 9 times negative 5, which is going to be positive 90. So my y-intercept is 0, 90. All right, then let's find the x-intercepts. Now again, because it's already factored for you, this should be kind of, hopefully, more straightforward. So we have an x-intercept at negative 3, 0, and one at positive 5, 0. Now keep in mind, right, this is important, that you see that 2 right there, you know that this root is going to be a double root. So when I graph it, it's going to have a touch and turn at negative 3, 0. Now, my apologies. The 5 is just a little bit off the grid here. All right. Now, from here, I just do the end behavior. It's not something you have to do, but I like to do this before I go into my graphing calculator and type this out to see what it looks like, just so I can have an idea that I know what's going to happen. So remember, I care about the leading term, right? The leading term is going to be, actually, you know what? Let's just do the leading coefficient first, which is negative 2. And I care that that's negative. Now, the degree might be a little tough to find, or at least tougher to find. You can do it a couple of ways. You notice that I highlighted the 2, so that's x squared, and this is x to the first power, so 2 plus 1 gives you 3. You also could go to your roots, your x-intercepts. That highlighted one is a double root, so that's 2, right? So like 2 plus this is a single root, which gives you 3. All right, and I care about that it's odd. So if I were to sketch the end behavior right now, all right, remember odd is going to be opposite directions. So since it's negative, it's going to be top left to bottom right. So that's what I'm expecting when I go in and graph it. So let's go ahead and go to our graphing calculator on Desmos so we can see what it looks like and see if we can find any other points to help us plot this polynomial. So we have negative 2 times x plus 3 squared, and then x minus 5. Right? When you have trouble seeing it like this, you can zoom out. What I personally like to do is to duplicate it and make it a table. And then when I click this button here and move out of the way, it'll actually make it a little easier to see. Now, when I back it out, it's definitely easier to see. So you can see our 5, 0. You can see our negative 3, 0. And our y-intercept of 0, 90. So we've already got those points. You see our end behavior, right? Top left to bottom right. Looks like I got another point here. I've got 1, 128, 2, 150, and actually the local maximum here of 2.3 repeating, and then 151.704. Again, I'm not that concerned about this being exactly perfect, but just want to show you kind of where I should kind of start going down towards that other intercept. So we've got, remember something like this, right? Remember this is our touch and turn. Okay, and then we're going to get to, what did I say, it was 2, 150, I believe. Let me confirm. Yes, and then it's going to go a little bit higher than that. So it's 2.3 and then 151. So it just barely goes higher than that and then comes down towards our single root and then this way forever. So this essentially is the sketch that I would make for this. Okay? All right, now let's go the other way. Now that we've shown how you can sketch it, now we're going to use our understanding of the multiplicity, the end behavior, and all that stuff to help us figure out what these are in terms of writing them if you're given the graph. So the first thing I do is I just find my x-intercepts, so negative 3, 2, and 5. So I'm going to write down f of x equals, write a letter A. That's going to be that leading coefficient that we're going to have to find by plugging in this y-intercept of 0, negative 2. So that's going to be the point that I end up caring about. So times, now watch what I put here, x plus 3. So always think opposite when you write down these roots, right? It's whatever makes them 0. So think opposite. And then I have x minus 2, and then I have x minus 5. Now, before you start moving forward trying to find your leading coefficient, take a moment and ask yourself, are any of these roots going to have a multiplicity other than 1? So, right, this one is, I would say this one is single, right, completely crosses with no s. This one looks like it's touching and turning, so I'm going to say double. And that one completely crosses, so I'm going to say single. So when I write my x minus 2 term, that should be raised to the second power. All right, so now I'm going to plug in y is negative 2, so replace that with negative 2, and then my x is going to be 0. We'll be ready to use our algebra to figure out what that coefficient is going to be in front of a. So 0 times 3, or 0 plus 3 is 3. 0 minus 2 is negative 2, but negative 2 squared is 4. 0 minus 5 is negative 5, and that's equal to negative 2. So I'm going to write, let's see, That's going to be negative 60 times a. So if I move over the negative 60 with division, I get positive 2/60ths, which reduces to 1/30th. So my answer here is going to be 1 over 30 times x plus 3 times x minus 2 squared times x minus 5. All right, let's do that same process for this next one. Find those roots. So negative 1, positive 2, positive 4. So let's write down, we have x minus 1, x plus 1, x minus 2, and then x minus 4. All right, so this is a touch and turn, so I'm going to say a double. This one looks like it is completely crossing, but it has that inflection point, so I'm going to say a triple root. You could disagree with me and think this is like going to be to the fifth power. I don't really know how to honestly tell that. It looks like it's flattened just like the letter S, so I'm going to say triple, but if you wanted to say to the fifth power, that's fine. And this completely crosses, so I'm going to say single. So this one is squared, this one is cubed, and then x minus 4 is going to be to the first power. Plugging in our 0, negative 4 for the y-intercept. All right, so now we have a times 0 plus 1 is 1, 1 squared is 1. 0 minus 2 is negative 2, negative 2 cubed is negative 8, and 0 minus 4 is negative 4. So this is going to be a times, let me put it in front. So that's going to be positive 32. So to move that 32 over with division, you get negative 4 over 32, which reduces to negative 1/8. So my answer with my a now is negative 1/8 times x plus 1 squared times x minus 2 cubed times x minus 4. All right. Now, one thing I forgot to mention as I look at both of these, if you look at in the first one, the letter A was 1/30th, right? You have this A is a positive 1/30th. And when you look, you should see that our degree is going to be single plus double plus single, which is going to be 4. So they're opening in the same direction, and a positive leading coefficient means they both go up. If you look at this last one that we just did, we had negative 1/8 became our A. Again, if you add double root, triple root, single root, that gives you 6. So that's an even degree. So they're opening in the same direction. And because our A value was negative, they're both going down for the end behavior. So just kind of a refresher of why those kind of match up for our letter A's. All right, so that's it. Make sure you are trying those example problems, and good luck.